So today we're talking about the pH and the POH scale. We're going to start with pH. The H in the pH stands for the concentration of the hydrogen ions. And most of you are probably pretty aware of that. A high pH means there is a low acidity, which means that our hydrogen ion concentration is low. A low pH means that we have a high acidity, and that means that our concentration of our hydrogen ion is high. So you need to remember that although the pH scale um, is pretty simple, it can seem a little confusing because it kind of does the opposite of what hydrogen ion concentration does. The other thing that can be a little confusing about the pH scale is that 1 unit of change doesn't mean it's changing by an amount of 1. 1 unit of change actually represents a 10 times change in the pH. So let's say we were looking at this change here, which is going from pH 7 to pH 6. Well, first of all, if our pH is going down, decreasing from 7 to 6, then the concentration of the hydrogen ion must be increasing because they move opposite of one another. And because it has moved 1 unit, it changes by 10 to the power of 1. So the hydrogen ion concentration increases by 10 times. Now, if we have our next example, you can see it's changing. pH is changing by 2 units. It's decreasing by 2 units. Therefore, hydrogen must be increasing by 10 to the 2. So in other words, it increases by 100 times. An example going the other way, we are starting with pH 8 and increasing to pH 11. So that's a difference of 1, 2, 3 units. So the hydrogen ion concentration is going to decrease because pH increased. And because it went by 3 units, it's going to change by a factor of 10 to the 3, which means that the hydrogen ion concentration, oh, for God's sake, snooze. Okay, okay, well, whatever. Okay, so hydrogen ion concentration is going to decrease, and where was I? pH went up by 3 units, so hydrogen ion concentration is going to decrease by 10 to the 3. In other words, it's 1,000 times lower. I would actually say it's probably better, maybe even, to say it's 1/1000th times what it was originally. Now, to have a very low pH, you've either got to have a strong acid, okay, because strong acids, because they dissociate completely, they will produce a high concentration of H plus at most concentrations. If you want to have a very low pH with a weak acid, that weak acid is going to have to be very concentrated. That's going to make up for the fact that so few particles of the acid actually dissociate. And here's just a little summary of that with cute little pictures. So we're looking at this table on the next page, and we can see that if I look way out a large view on this, we have acidic pHs, which is from 0 to 6, although that's a little bit deceptive actually, because the pH range will go below 0. So if we make this a little bigger, we can actually write that it goes to, oh, maybe I'll even make a little circle here and a little circle here. It can go down to -1, it could go down to -2, and a pH doesn't actually have to be 6 or below to be acidic. Even if it is at 6.99, that would be considered very, very slightly acidic compared with pH 7. So if we have an acidic pH, that's going to be any pH that is less than 7. So in other words, a low pH is acidic. In the middle, where we have pure water, that's going to be a neutral pH. Okay, so pH 7 is neutral. Anything above pH 7 is alkaline, or another way of saying alkaline is basic. Basic, there we go. So a basic pH is anything above pH of 7. So a basic pH is pH greater than 7. In other words, a pH is high if we have a basic pH. This is only true at 25 degrees Celsius. At different temperatures, the pH scale changes. We'll talk about that in a later lesson. A few other things that we can see on here. First of all, we can take a look at some of our examples of products, everyday examples that are alkaline. And you'll notice we have drain cleaner, bleach, ammonia, and soap. All 4 of those are some sort of cleaning product. And I don't know if you were in one of the discussions where we were talking about accidentally tasting soap, but soap has a bitter taste. So that's one way you can know that it is alkaline. The other thing is that bases are slippery, and so that makes them good cleaning products because it helps the dirt slip right off of things. Down in our acids, you'll notice we have some fruits and fruit juices down here. Fruits and fruit juices. Okay, we also have coffee, stomach acid, yuck, that's why it tastes so terrible coming up, because it's a pH of 1, and battery acid, which is, in your car battery. Just as I said, the scale can go below 0, it can actually go above 14 as well. So I'm just going to kind of go, okay, we could have a 15 or a 16. It's really rare to get pHs above 14 or below 0, which is why we don't see them very often, but it doesn't mean they can't exist. Other things we want to notice about that. What's happening to our hydrogen ion concentration as the pH decreases? As pH decreases, the hydrogen ion increases by 10. Okay, so every time pH decreases, hydrogen increases by 10 times. What do you notice about the OH concentration as hydrogen ion concentration is increasing? So hydrogen is increasing as we go down. As we go down, hydroxide is decreasing by 1/10 every time we go down. And so what we'll end up with then is as a hydrogen ion concentration goes up, the hydroxide ion concentration is going to go down. And when they meet in the middle, oh look, at pH 7, the concentrations are both 1 times 10 to the minus 7. All right, back to here. So, takeaways from the table. As pH increases, the hydrogen ion concentration does the opposite, it decreases. As pH decreases, the hydrogen ion concentration increases. As hydrogen increases, hydroxide decreases. And as hydrogen decreases, hydroxide increases. So those are all inverse relationships. Now think about this for a moment. pH is a logarithmic scale. If you don't know what that means, we will talk about the mathematics a little bit more in a later class. But from what you noticed on that table, if pH doubles, Does the H plus ion concentration double or does it not double? Think about that for a minute. Look at your table if you need to. The hydrogen ion concentration does not double every time pH doubles. Instead, for every change in the unit of pH, the hydrogen ion concentration changes by a factor of 10. All right, an example here of what happens when we change the pH. Let's say our pH increases from 2 to 4. What has happened to the concentration of hydrogen? Well, if we go back to our chart, a pH of 2, where'd it go? There we go. It corresponds to 0.01, which if you recall is 10 to the negative 2. Okay, so back here. So if we have a pH 2, hydrogen ion concentration is 10 to the negative 2, which means the molarity is 0.01 molar, if we want to write it that way. If we have a pH of 4, our hydrogen ion concentration is 10 to the negative 4. Oh my gosh, look at that. pH 2 is 10 to the negative 2, pH 4 is 10 to the negative 4, pH 5 is 10 to the negative 5. Hopefully you're going to see a pattern here as well. So let's go back and fill that in. So at pH 4, hydrogen ion concentration is 10 to the negative 4 molar, which is 0.0001 molar. So when our pH increased by 2 units, our hydrogen ion concentration decreased by 10 to the 2. In other words, it changed by 1/100th. It got smaller by 1 over 10 to the 2. So the pH has decreased by a factor of 1/100th times. If a pH of a solution has decreased from 7 to 4, okay, so we have pH, and it's decreasing from 7 to 4, what happens to hydrogen? Well, first of all, our corresponding hydrogen concentrations, that's going to be 10 to the negative 7 molar and 10 to the negative 4 molar. So the difference between those two is 10 to the negative 3 molar. The important bit here is not so much the sign of the power of 10 is that it is 10 to the 3 of some kind, and we know that hydrogen ion concentration has to increase, and so because this was a difference of 3, hydrogen ion concentration changes by 10 to the 3, and because it was an increase, hydrogen ion concentration, you can say, increases by a factor of 1,000 times. Okay, had it been decreasing, we would have said 1 over 1,000 times, but it was increasing, so there we are. Next, we have another scale, very, very similar. It is the POH scale and is simply the opposite of the pH scale. This is a really nice one right here, so you can always come back here and refer to things as you want to. So you'll notice that as pH goes up, POH is going down. Everything is directly reverse. Okay, taking a look at some of these things. At the same level of acidity or basicity, what is the sum of the pH and the POH? So what we have to do is we have to add the two. So what we have to do is we're going to take a look at these two and we're going to add them together and we're going to get 14. Oh, Nice. Let's add 13 and 1. What do we get? Oh, we get 14. Let's try some other ones. How about if we add 7 and 7? We get 14. We add 8 and 6. We get, oh, I got 7 and 7 and got 7. It should be 14. 8 and 6, we get 14. 9 and 5, we get, oh, guess what? 14. So at 25 degrees Celsius, pH plus pOH is equal to 14. And this is true only at 25 degrees Celsius. At other temperatures, this number will be different. So at other temperatures, this number is going to be different. pH plus pOH will equal something different. We'll talk about that in a later class. Also different at a temperature other than 25 degrees. At a temperature other than 25 degrees Celsius, neutral pH is not 7. Okay, so that's what we've got there, and that we'll again learn more about that later. It has to do with the shifting of the equilibrium due to temperature. Ooh, temperature shifts the equilibrium. So, familiar. This number 14 has a name attached to it, or a symbol. It is called the pKW. Just like we have pH and pOH, this is our pKW. And KW is the KEQ for, not for the ionization constant of water. Not for the ionization constant of water, for the ionization of water. And if you're wondering what that is, if you take H2O, a very, very tiny bit of it actually does dissociate into H plus and OH minus. And again, we'll talk more about that later. These terms, pKW, KW, the ionization of water, all of those are things that are not going to be on your quiz on Friday, but they will be ideas that you're going to need to know for over the break and after the break. Next question. At the same level of acidity basicity, the product of hydrogen times hydroxide is always equal to what value? Well, when we multiply 2 powers of 10, we add their exponents, and so we have 10 to the negative 14 plus 10 to the 0 is 10 to the negative 14. 10 to the negative 13 times 10 to the negative 1 is negative 13 plus negative 1 is 10 to the negative 14. We can go down the whole list, and once again, we're going to get a consistent value all the way down. The product of hydrogen times hydroxide is always 10 to the negative 14. So, concentration of hydrogen times the concentration of hydroxide is equal to 10 to the negative 14. Or we could say 1.0 times 10 to the negative 14. This value here is actually Kw, which we just talked about. If we have water, H2O, and it dissociates just a tiny little bit into H plus and OH minus, then the K value for that, of course, we have hydrogen times hydroxide, there we are, and we get 1 times 10 to the negative 14. This value actually shows up on your data booklet page. There we are, that's the one. And if we look, here is they call it the auto ionization of water. Auto meaning something one does to oneself. So the auto ionization of water is given right here. And here we have 10 to the negative 14, and that is kW. So what's the takeaway message from this page? Well, if you know hydrogen ion concentration, then you can use kW, the value, which doesn't change unless you're at a different temperature than 25 degrees Celsius. So I guess I should say at 25 degrees Celsius. You can use that to find the concentration of OH, and so you just have one unknown. Similarly, if you have your pH, say you know your pH, and your POH is unknown, then you have 10 to the positive 14 there. Okay. All right. What's next? If you are given the pH, how can you find the hydrogen ion concentration? So how do I take 14 and get 10 to the negative 14? So how can I calculate hydrogen ion concentration if I'm given the pH? Well, all I do is I take the pH and I put 10, and then I raise 10 to the power of whatever the pH is, but I make it negative. So hydrogen ion concentration is 10 to the negative pH. Cool, yes? If you are given the hydrogen ion concentration, so this time we're going the other way, how can I find the pH? Well, I don't know how familiar with logs you are, but the log of, sorry, the log of 10 to the x is x. So if I were to take the log of the hydrogen ion concentration, I would get, let's say we're looking at our value here, 10 to the negative 10. So the log of 10 to the negative 10, in this case, negative 10 is our x value. So that would equal negative 10. Is that what we got for our pH? No, our pH isn't negative 10, it is positive 10. So if we actually have our hydrogen ion concentration, not only do we have to log it, but we also have to make that value negative. So the negative of the log of hydrogen is the pH. So let's try that out. So if I have the negative of the log of, let's say 10 to the negative 3, 10 to the negative 3, then that's equal to the negative of, well, what am I doing? There we go. The log of 10 to the negative 3 is negative 3. So I have the negative of negative 3, which is 3. Oh, look at that. Very cool. If you're like, well, that was a little complicated, I'm not sure I'm going to remember that just yet, don't worry. Monday's lesson will deal with all this math stuff in depth. This is just to introduce you to it while you're looking at the scale, okay? All right, and now if you are given the POH, here's our POH, 13, let's say, how can you find the concentration of OH? Well, this is really similar, yes? If I have the POH is 13, then my concentration of hydrogen, or not hydrogen, hydroxide, is 10 to the negative 13. So if in general, my concentration of hydroxide is 10 to the negative POH. Okay, so you notice the same thing about those two formulas. Hydrogen ion concentration is 10 to the negative pH, and hydroxide ion concentration is 10 to the negative POH. If you are given the hydroxide, how can you find the POH? Well, again, this comes down to it's a little bit confusing, possibly if you're not super duper with logs, but if I give you, say, a concentration of OH equals 10 to the negative 9, well, if I take the log of that, log of 10 to the negative 9 is negative 9. So that doesn't quite get us there because we wanted to get a value of 9 for our POH. So instead of just taking the log, we have to take the negative log of 10 to the minus 9, which is then the opposite of negative 9, which is 9. Oh, gosh, look at that. So what does that mean we have here? It means that we have that the negative of the log of hydroxide is equal to the POH. Again, just introducing these concepts. Monday's lesson will be all about this, so you'll feel much better about it after that. We have done some examples of this before. So if you are feeling like I'm going to skip over it for now. I will come back to it later, so you can just skip this if you feel good about what changing hydrogen, or sorry, pH means in terms of changing hydrogen ion concentration. Finally, a practical application of the pH scale. We're looking at the acidity of rainwater. So the acidity of rainwater, we have rain in streams is a pH 5.5 to 6.0. Wow, that's weird because neutral, this is pure water here. Pure water has a pH of 7. But rains and streams are slightly more acidic than that, which means they cannot be pure water. They must have something else inside them. And what that something else is, it is dissolved carbon dioxide. Okay? Dissolved carbon dioxide reacts with water and it produces carbonic acid. You are responsible for this equation. It's fairly straightforward though. If you can remember that there's lots of carbon dioxide around and that reacts with water, if we look, we have one carbon, we have two oxygen, we have two hydrogen, and we have one oxygen. All we've done is we've taken the one carbon there, we've taken the two oxygen and the one oxygen, and we end up with three oxygen, and we have the two hydrogen, which gives us two hydrogens. So we're basically taking CO2 and H2O and cramming them together into one formula. Okay, so this dissolved carbonic acid is why the streams are mildly acidic. H2CO3 is a weak acid, so this is why the streams are only, and rainwater are only mildly acidic. If we go to our data booklet and we look up carbonic acid, H2CO3, there it is right there, kind of near the middle but lower than the middle. It's got a Ka of 4.3 times 10 to the minus 7, so it's not too acidic, which is why regular rainwater and regular streams are not particularly acidic, just a little bit, pH 5.5 to 6.0. Now, acid rain, which is a fairly nasty problem, is significantly more acidic than normal rain, and that is due to dissolved SO2 and SO3. And the SO2 and SO3 comes from burning coal, which has sulfur impurities. Okay, so when we burn them, they get oxidized, oxygen attaches onto the sulfur, and we do the same thing with the sulfur dioxide and the sulfur trioxide, is we react them with water and we just cram the whole thing together into one formula. So we have one sulfur, two, three oxygen, and two hydrogen. So we end up with H2SO3. This acid here, this is sulfurous acid. It's a weak acid, but it is a little on the stronger side than HCO3, so it does make acid rain more acidic than normal rain. Now, the big problem, though, from burning the coal with those sulfur impurities is not the SO2, but the SO3. And the problem with SO3 is that when we cram it together with water, we end up with 4 oxygens in total, which is going to give us H2SO4. And that is sulfuric acid. H2SO4 is a strong acid, and remember, strong acids are so much more acidic than weak acids. Okay, and that is the main reason why acid rain, if we go back up here and we take a look, acid rain isn't just slightly acidic. Acid rain is very acidic. It's in this pH 2 to pH 4 range, which is kind of nasty. Yes? I mean, technically anything below 5.5 is acid rain, but it starts to get really nasty in that pH 2 to pH 4 range. Okay? There is another source of nasties for acid rain, and that is NO2, nitrogen dioxide. And that is from burning fuel in a car, burning gasoline in a car engine. Okay, and so this reaction is a little bit more, it's a little bit less straightforward. So if you don't remember this one, it's not a big deal. If you can remember the other three, the carbonate, formation of carbonic acid, the formation of sulfurous acid, and the formation of sulfuric acid, you're good to go. This one is a little trickier, but if you look and say, I have a nitrogen and oxygen compound, NO2, and if I go to my data booklet, which acids can I find that have N's and O's? Well, let's go look. Oh, there's HNO2 right there, and there's HNO3 right there. HNO3 is a strong acid. HNO2 is a fairly strong weak acid. So between the two of those are significant contributors to the acidity of acid rain. But one thing you can do is you can predict the products of reacting NO2 with water by saying, I know I'm going to get both of the two NO acids that are on my data booklet. So going back, I know I get both of those acids that are on the data booklet, and in order to get both of them, I need to react two NO2s. Okay? In general, you should know that non-metal oxide gases produce acidic solutions. Okay, that's a generality. Okay, and that is it. And maybe we could actually, we'll leave the questions for Monday. How does that sound? Yeah? Or, well, why don't you do like questions 1, 2, and 3? There you go. Questions 1, 2, and 3. Excellent. All right. Have a good weekend.